Algebra 2, here are your notes for 7.2 inverse functions. So the first thing is, do you remember what the relationship is between a relation and its inverse? For instance, if we look at this set of coordinates, what is the inverse of the relation? Well, if you recall, the inverse of a relation just takes whatever was in the y position and turns it into the x. And whatever was in the x position gets turned into the y. And then the same thing happens for all of our coordinates. Notice no negatives change, no positives change to negatives, nothing like that. We literally are just swapping our x's and y's. And that's going to be really important to remember. Whatever was an x becomes a y, whatever was a y becomes an x. So log that fact away, throw it down as a note over here, whatever you have to do, but it's going to come in handy in a little bit. So now what we're going to do is we're going to take that and we're going to complete the tables here to look at what inverses look like graphically. So with this first one, if we're looking at the function f of x equals x squared, where x is whole numbers, it doesn't really matter what we choose as long as there's no fractions involved. So I'm going to do the really easy thing and just go 0, 1, 2, 3. And then I can just plug them into f of x. 0 squared, still 0. 1 squared, still 1. 2 squared becomes 4. And 3 squared becomes 9. Let's start throwing those on our graph. 0 stays at 0. 1 goes to 1, 2 jumps up to 4, and 3 jumps all the way up to 9. And then if we plot this, connect the dots, it's going to look something like this, kind of like half of a parabola if you can see that a little bit. Now let's jump over to our next graph. We talked about earlier in the year about how x squared and square roots were inverses of each other. A square root undoes a square, and squaring something undoes a square root. So, in theory, these two graphs should be inverses of each other. Notice, when we're completing this problem, x has to be a non-negative perfect square. So it's not quite as easy as going 0, 1, 2, 3. In this case, 0 is a perfect square, so that one we're okay with. 1 is a perfect square, we're okay with that. But if we take the square root of 2, we're not going to get a nice number. So I'm actually going to go ahead and jump up to 4 because I know that it becomes a nice number when I take the square root of it. Same thing, if I try to do a 3, it wouldn't be a nice number. So I have to jump up to my next nice square root, or perfect square, of 9. And then, of course, I'm just going to take the square root of these. The square root of 0 of 0. Square root of 1 is 1. The square root of 4 is 2, plus or minus, but in this case, we're only talking about the positive. And then, of course, 3. Now, before I've even graphed it, you should notice something. Do you see how the x of your first function became the y of your second function? The y of your first became the x of your second? That shows me that these two are, in fact, inverses of each other. So let's see what that looks like graphically. 0 stays at 0, 1 goes to 1, we jump all the way over to 4, and then jump all the way over to 9, and connect the dots. There we go. Now what I'm going to do is I'm going to take this even one step further and show you something that I really like to see. Let's pick a different color here quick. I'm going to bring this graph in pink over onto this graph so that you can see it. 1 goes to 1, 0 goes to 0, 2, 4, 3, 9. And then I'm just going to sketch this in. Now, why did I do this? Well, the reason is because I want you to see why they're inverses. If I drew a dotted line right up the middle of these, you would see that they are a nice mirror image of each other. We really like that because they are mirrored over what we call the identity function, meaning I of x equals x. Essentially that means any inverse we ever have will always be mirrored over this line. It will always be mirrored over the line y equals x. Again, something fun to log away for later because it'll come in handy. This is what do you notice about the graphs and what do you notice about the ordered pairs? Well, I kind of already touched on that. I already noted that my x becomes my y and my y becomes my x in the ordered pairs. What did you notice about the graphs? Well, they're mirrored over the function y equals x. If you want to write down some other other facts that you notice, please do that. I think I've kind of covered the ones that I think are important, but if you see others, shoot me an email too. I'd love to know what you see that I don't. Let's keep going then. Suppose f and f inverse are inverse functions. Then f of a equals b if and only if f inverse of b equals a. Guess what? That's super crazy math language. It's got an if and only if in there. Here's the thing. It's not that scary. All it says is that they're only inverses if they're inverses. We can flip them over that identity function and their y's become their x's and their x's become their y's, that is an inverse function. So let's see what this looks like. Let's ignore that concept for a minute and just start working with the math. Find the inverse of f of x equals x plus 6 over 2. How do we do that? It's actually not that hard. The first thing I'm going to do is I'm going to replace f of x with the variable y. I just prefer that. It looks a little bit nicer. X plus 6 over 2. Now we know, based on what we just set up here, that x's become y's and y's become x's. So if we ever need to find the inverse of something, all we're going to do is switch out our x and our y. Where it used to be equal to y, now it's going to be equal to x, and where there was an x in my function, I'm now going to place a y. That seems weird. It seems like I'm just arbitrarily doing that. But watch this. Let's first start off by solving this for y. We don't know how to graph things that are equal to x, but let's solve this. I multiply both sides by 2, so I have y plus 6 equals 2x. I then move the 6, and I'm left with y equals 2x minus 6. That is a function we can graph. That I can make a table for or just throw it on here. This one may look a little more foreign. You might want to go to a table for this. However, watch this quick trick. If these two pieces above are over the same denominator, there's no rule saying that we can't break this into two fractions. i.e., this is the same thing as 1/2 x plus 3. All I did was I said, I know the left side is x over 2, I know the right side is 6 over 2, and I rewrote it like this. Now let's actually graph these. If you want to make a table, you can. I'm not going to for this one just because I think these are simple enough to graph. So let's get some fun colors for this. Let's grab something here. Here's a purple one. All right, we're going to do this one first. Y equals 1/2 x plus 3. Quick throwback to your algebra days. We're going to go up to 3 and then go up 1 over 2, up 1 over 2. And I don't think... Nope, I don't have a straight edge on me, which is unfortunate, so I'm going to have to freehand it unless I can find a straight edge. You should all be disappointed in your math teacher right now. She doesn't have a straight edge on hand. All right, here we go. There's one. There. Without having a straight edge, that was pretty good. All right, so there's your first line. Let's do the other line and see what happens. This one we're going to do in pink. Go down to -6. Up 2 over 1, up 2 over 1. And we're going to keep going. And then again, we're just going to connect those dots. That one one was a little rough, but you get the picture. All right, so there are your functions. Now, since we've graphed them, let's see if it still follows our rules. This point is at 0, 3. On my inverse, it becomes 3, 0. This point is 2, 4. On my inverse, it becomes 4, 2. So it already follows the rule of my y's equaling my x's and my x's equaling my y's. The second thing to check is, does it mirror over the identity function of y equals x? Well, if we draw our identity function right down the middle, you'll notice if we put a mirror right in the middle there, both halves would mirror perfectly. So we graph these correctly. Hopefully that's not too hard. Let's jump to the back and see what that's got for us. So how can you quickly tell if two functions are inverses of each other? Say you don't want to go to all this graphing work. Well, what we can do is we can use composite functions to make our job a little bit easier. And one thing I want you to write down in some space, I'm going to put it right here actually, is this rule. So, if the compositions of both of f and g, so of both functions, if the compositions of both functions, i.e. this is the same thing as fog and goff, if the compositions both equal x, they are inverses. Then they are inverses. All right, lots of words. Here's what it means. Let's take g of x and f of x. The first thing I'm going to test is fog. What I'm going to do is I'm going to take my f of x function and I'm going to plug in my g of x. The same way that I was doing on the last page and then in the previous video. 2x plus 8 gets plugged in. So there I have calculated fog. And when I simplify it, I get 1/2 times 2x. That's just x. 1/2 times positive 8 is 4. 4 minus 4 is 0. So I'm left with x. Notice the composition for f of g is equal to x. That's a good thing. However, this says if the compositions of f and g both equal x, meaning I can't just check f of g, I also have to check g of f by plugging in. I take g of x and I plug in f of x. 1/2 x minus 4 plus 8. All I've done is take my f of x and plug it into my x. And same thing. 2 times 1/2 x is x. 2 times negative 4 is negative 8. Negative 8 plus 8 is 0. And we're left with x. Notice both compositions are x. So these are inverses. This is a lot faster than graphing every single set of functions you're given and then trying to see if they both map over the identity function. I would much rather solve 2 quick compositions than graph every time, but that's just me. I want you to try the second one on your own, so pause the video now, give that a shot. My hint to you is that if you do this one right, it will not be an inverse. So, see if you can do that on your own, and then come on back and we'll try it together. Alright, hopefully you paused the video long enough to try those compositions and find out that they are not inverses. Let's do it together. F of g, we're going to take our f of x function, 3, and plug in our g of x function, plus 4. When I simplify this one, I am going to get 9x minus 8. Already, this does not equal x, which means it's not an inverse. But for the sake of being thorough, because we are thorough mathematicians, I also am going to calculate g of x to make sure. 3 outside of 3x plus 4 minus 4. This becomes 9x plus 8. That one doesn't equal x either, so we are not good there. These are not inverses of each other. So I think that's kind of a handy little rule. All right, last two on this page. Find the inverse of the function. We already did this on the last page, but I do want to do a quick review of it, just so you've seen a second example. Remember, our first step is always going to be rewrite it with a y instead of an f of x. This allows us to then, in our second step, switch out our x and our y. So if you're following along in steps, first step, rewrite with y. Second step, switch x and y. Third step, solve for y. In this case, I have 1/3 y equals x minus 4. Multiply everything by 3 to get rid of this 1/3. And I am left with y equals 3x minus 12. This would be the inverse of f of x. We could also notate this as f to the -1, aka the inverse, in this fashion. Both of these would be correct. I personally don't usually waste time writing this one, but I would like you to see that notation and get comfortable with it. All right, last one. Determine whether the two functions are inverses of each other. We just did these twice, so I would encourage you again to pause the video, give these a shot on your own, and then hop back in and try. But I'm going to go right into them. So pause it if you want to, or just keep watching. All right, first we have to find h of g. That one is going to be 5 outside of, and I'm going to simplify this just because I don't want to put in that many parentheses. So it'd be 1/5 x plus 7/5 minus 7. That equals, this is 1x, that would be positive 7 minus 7, so that equals x, which is good. And g of h, which would then be 1/5 outside of 5x minus 7 plus 7/5. Simplify, this becomes x, that becomes negative 7/5 plus 7/5 is 0, and it becomes x. Both of these work, so they are inverses. All right, I feel like I threw a lot at you in this video. There's about 4 new skills in here. So remember, practice makes permanent. Practice, 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 and please let me know if you have any questions.